Alrighty, so I'm just going to basically talk about some reaction stoichiometry here. This should be really familiar to you if you've attempted your summer assignment and checked yourself with the answers. I'm going to talk about balanced chemical equations, percent composition, actual yield versus theoretical yield, and limiting reagent. So the reason we should balance equations is because we want to abide by the law of conservation of matter or mass. Whatever we have on the reactant side, we should have on the product side. So we have ammonium dichromate here, yielding chromium 3 oxide, nitrogen, and water. We balance this. It's actually already balanced, except for we need a 4 here on the water because we have 4 hydrogens here, actually 8. We need to have 8 over here. This next example is actually going to be decomposition. Because we only have one reactant, we need to break it down into its elements here, and it's going to be made of H2, which is diatomic hydrogen, and O2, which is diatomic oxygen. But to balance that, we need to make sure that we have 2 hydrogens, 2 hydrogens, 2 oxygens. We don't have 2 oxygens, so we need to put a 2 out front, meaning we need a 2 right here. So this is actually done through electrolysis. I mentioned this in another lecture, so that should be familiar to you. We've got calcium chloride and sodium phosphate. This is going to be a double replacement reaction where we have calcium and sodium pretty much are going to be exchanging their places here. So we can make calcium phosphate. To make sure I write my subscripts really well so you can see this. And sodium chloride. And we need to balance this by putting a 6 on the sodium here and 2 over here. So we have 6 sodium atoms, 6 sodium atoms, and a 3 in front of the calcium because we had a 3 coming from the phosphate's charge. Lastly, we have a combustion reaction. We should know that carbon dioxide and water are made in combustion reactions. And then usually what I do is I look at the carbons and I see I have 3 carbons over here, so I need 3 here. But we also want to make sure we're going to be satisfying the hydrogen's content. So I see 8 here, I see 2 here. So if I put a 4 here, that's going to satisfy the 8. If I put a 3 here, it's going to satisfy the 3. And then lastly, my oxygens, because I can put any number over here, I just need to make sure I have an even number on this side. So just a trick there, you want an even number of oxygens on the product side when you're doing combustion reactions, so you can balance that with a whole integer. So we have 4 here, we have 6 here, so I have 10, so 5 times 2 is 10. Alright, so usually leave your oxygen for last. Alright, so percent compositions related to a specific element that we have in a compound, and we want to know what percentage of the entire compound does that element make up. So I have an example here for you of kind of how we do the mathematics. You take the number of atoms, so looking at the subscript of that element in the compound, multiply by its atomic mass, so you need a PTOE for that, divided by the molar mass of the entire compound, times 100 because it's a percent. Okay, so what's the percent composition of potassium dichromate? First of all, we should all know potassium dichromate is K2CR2O7, because this is dichromate. The 2 here is coming from the dichromate's charge. When I want percent composition, that means I need to know of each of these elements of potassium, of chromium, and of oxygen. So I know that for potassium, this is what I need. I have 2 potassiums because of the 2 subscript, each weighing 39.10 grams over a total mass of our compound, which is what we actually need to go ahead and calculate. So I know I have 2 potassiums, which is 39.1 grams, plus 2 chromiums, each weighing 52.00 grams, plus 7 oxygens, each weighing 16.00 grams. That gives us a grand total of 294.2. I'm going to say 20 grams. Okay, so this is our final molecular mass of potassium dichromate. All right, so 2 potassiums per that total, 294. Let's see, 20 times 100 to give us 26.58%. All right, same thing for chromium. Chromium's going to be 2 from the subscript here times 52.00 grams divided by the total mass of 294.20 grams times 100, making 35.35%. So technically here, you don't have to do oxygen the same way. You can, but we should know that percent composition should add up to 100%. If you add these two here, you take 100 minus these two, you'll get oxygen's percent. But if you want to do it the way we've been doing, then oxygen is equal to 7 of them times 16 grams, 16.0 grams, divided by 294.20 grams times 100 will give you 38.07%. All right, hopefully you can read that. Okay, so that's pretty easy, but if I ask you just generally the percent comp, I want you to do it for every single element present in that compound. Another example is copper 2 sulfate pentahydrate. This formula you should know is copper's Cu, sulfate is SO4. This is a 2 minus, this is a 2 plus because of the Roman numerals here. That's just copper 2 sulfate. And then pentahydrate. Penta means 5, hydrate just means water. So we simply just draw like a little bullet here and then put 5 H2Os. So that's copper 2 sulfate pentahydrate. When you do this process out the same way that I previously have done, you'll get copper is equal to 25.46%. You can do this and check yourself. You get sulfur is equal to 12.84%. And you get oxygen equal to 25.64%. Now, I only did oxygen present in the sulfate here. Okay, I didn't use the oxygen from the water because in this case, for a hydrate, you're going to actually calculate the water's percent as a whole. Don't separate the H from the O here. So when you do water, 5 of them, so 5 times 18 is 90 grams. That's going to be 36.06%. Okay, so you can check yourself, try that out, and make sure you can do percent composition. All right, so these previous examples have been ionic compounds, so we always write ionic compounds in the empirical formula. For example, I didn't write Cu2SO4 2 because that looks silly, and I know that I can reduce this 2 and this 2 down to the lowest possible ratio of 1 and 1, which is why we write copper 2 sulfate as CuSO4. We don't write it like this because that's not how we write ionic compounds. We have to use a molecular or the simplest ratio. Covalent compounds, like molecules, we write them in empirical or molecular formulas, meaning we have a ratio here that can be reduced, but we don't care. We have molecular compounds can be in a multiple of that ratio. We'll do more empirical formulas and molecular formulas when we talk about combustion analysis. All right, so a little bit more about stoichiometry. You should be able to convert pretty much from anything. I can give you mass and I can ask you to go to moles of something or of something else, so you'd be using mole ratios. I can ask you from mass to mass, so you're going to have to go through a couple of steps in dimensional analysis. It just depends on what I need you to go to. You should be skilled enough to do that through basic stoichiometry. So if we're using some process of going moles of X to moles of Y, you're going to use your mole ratio. And where do you get a mole ratio? You get it from the Balanced Chemical Equation, or BCE. If I ask you to moles to mass of that same compound, you're going to use the molar mass of that compound. You just have to add that up. Same thing here. You're going to use molar mass. If you're going from mass to moles, you just need to invert that, remembering that grams per mole is how we write molar mass, but if you need to flip it in order to cancel units, you put moles over grams. And then from mass to mass, we can't go directly there. We have to go indirectly. Indirectly meaning we're going to go molar mass first, and then we might use mole ratio, and then we might use molar mass again, depending on what we have here present in our problem. So for example, we've got what mass of potassium iodide is Ki, is necessary to completely react with 20.61 grams of lead 2 nitrate in a double replacement reaction. So it's telling you what kind of reaction we have here. We know that potassium iodide reacts with lead 2 nitrate. Lead is Pb, nitrate, NO3. 1 minus, this is a 2 plus when you put a 2 down here. reacts. And it's going to do a double replacement reaction. So KNO3 is a product and lead 2 iodide. This is our precipitate here, and that's not a question here. Just know that an iodide is usually going to be insoluble with lead. It's a heavy metal. Okay, so we need to balance this. We see that we have a 2 over here. We need to put a 2 in front of the K. We need to put a 2 in front of this K, and 2 nitrates, check. All right, so what mass of potassium iodide? Usually what I start here is with the given. The given here is 20.61 grams of lead 2 nitrate. And I can't do anything with grams, so automatically I know I should be going to moles of lead 2 nitrate. So 1 mole of lead 2 nitrate is 331.2 grams of lead 2 nitrate. And I like to label all my identities, so sorry it takes me a minute here. Knowing this, I know that I can cancel out the grams of lead 2 nitrate. And I don't care about lead 2 nitrate anymore. I need to get to potassium iodide, so therefore I need to use the mole ratio now. The mole ratio is 1 lead 2 nitrate per 2 potassium iodides. So 2 moles of Ki over 1 mole of PbNO3 2. I put the PbNO3 2 on the bottom because I need to cancel out these moles of of lead 2 nitrate. My last step is get to the final question, mass. Mass is the question, or the unit here. So I need to know the molar mass of Ki. 1 mole of Ki actually weighs 166.01 grams of potassium iodide, and moles of potassium iodide can now be canceled out, and we should get, once we do our calculations, we put in our calculator correctly, we should get 20.66 grams of potassium iodide. If you thought you knew that, you did really well. Congrats. This is a pretty easy problem. Just make sure you use your units correctly. All right, example number 2. What mass of solution? So this is kind of phrased weird. Mass of solution, not mass of any particular compound. That is 22.5% potassium iodide is needed to completely precipitate out 0.28 grams of lead 2 iodide. All right, so this pretty much is this is our given. This is what we should be starting with. This is going to be miscellaneous for the moment, and then we're going to use it shortly so that we can get to mass of solution. Usually the first step for any type of problem is to write out the BCE. So here we go again. It's the same as before. Ki plus Pb. Actually, it is the same problem. Okay. Lead 2 nitrate. I just didn't specify it here. Yielding KNO3 plus lead 2 iodide. There's our precipitate. We need a 2 here and a 2 here. Okay. I'm going to start with our given of 0.28 grams of PbI2. And the reason I'm using this is because it says precipitate, okay, of lead 2 iodide. Okay. And then I know that I really can't use grams initially. I need to go ahead and convert to moles. Usually that's going to be our first step. So 1 mole of lead 2 iodide has a molar mass of 461.02 grams of lead 2 iodide. Here is my problem. I don't need lead 2 iodide anymore. I actually need to get to potassium iodide, which means mole ratio. So I've got a 2:1 ratio. So 1 mole of lead 2 iodide for every 2 moles of potassium iodide. I'm going to ignore the whole mass percent of solution right now and just figure out how many grams of potassium iodide I need, because grams is referring to mass, and that's going to allow me to get to mass here shortly. All right, so 1 mole of potassium iodide, its molar mass is 166.01 grams of potassium iodide. And I'm going to stop here and get my calculation of grams to be 0.2017. I carry this out a little bit because I don't want to have any rounding error of Ki. Okay, this is not the solution. This is simply grams of potassium iodide. So now I need to figure out, of that solution, that's 22.5%, how much of that do I need in terms of mass? So here's kind of how I set it up. 22.5, I'm not going to put grams there. Let me get my eraser. 22.5, I'm just going to make a ratio, over 100. That's the 0.225 is going to be the percent, times some value that I need of that solution is going to give me 0.2017 grams of potassium iodide. Okay, this is my question. This is the massive solution that I need. So what I should be thinking is, if, let's call it 25% just to make it easy. If 25% of a solution is potassium iodide, then 25 goes to 100 4 times. This should be approximately multiplied by 4, which would give us about 0.8. But we know it's going to be a little smaller than that because that's not 25%. When you do your math, you multiply by 100, divide by 22.5, you'll get x is equal to 0.2017 times 100. I'll show you my math. Divided by 22.5 to give me 0.896 grams, and I'm actually now going to round to 0.90 grams of solution. So I lied to you. You need a little bit more because of the fact that it's got a lower percentage. Okay, so now I use 2 sig figs because of my 2 sig figs present, and initially that's going to be limiting me throughout the entire problem. So that's our right answer. This is just the basic definitions of yield types. We'll be using this when we talk about limiting reagents. So theoretical yield, this is kind of, I call it the la-la land yield, because we don't actually ever get our theoretical yield, because most of the time there might be some imperfections in the lab procedures. If you get really close to your theoretical yield, then you're awesome, but it usually doesn't happen, but it's our comparison point. Actual yield is our for real experimental value, and this is what we actually get in the lab because of some lab experiment. Maybe some error, maybe the fact that the chemicals just don't have enough kinetic energy or energy to meet the activation energy of the reaction. It's just going to be what we have present here. I don't know what that is. Okay. Percent yield is actually going to be just a actual yield over theoretical yield. Is just an equation. You need to know this. I ask you a lot in the lab, what's your percent yield? If you have like 95% yield, that's amazing. If you have 70% yield, that's not so great. So this is where we will be working on our lab skills. The thing that limits a reaction or limits the extent of reaction is called your limiting reactant or limiting reagent. It's the same thing. I usually will label this as LR. The excess reagent is the one that you're going to have excess of. You're going to have more than enough of it in comparison to the limiting reagent. So you're going to use up all of this in the reaction. There will be none left because it's the limiting reagent. You're going to use it up entirely. The excess reagent, there will be a surplus or some excess of it left in the end. So I always label excess reagent as XS. All right, let's do a problem involving this. In an experiment, a student collects, this is just percent yield, collects 8.7 grams of ammonia from the reaction of 9 grams of nitrogen with excess hydrogen. So this is not really a limiting reagent problem because it literally tells you hydrogen is in excess, meaning nitrogen must be the LR. What's the percent yield? All right, so we know for percent yield we need actual over theoretical times 100. But we need to figure out, we know that this right here is going to be a given. We also know if we read the problem correctly, the student collects this many grams of ammonia. This is our actual yield because it's telling you that in the lab they are actually collecting this many grams of ammonia. All right, so let's go ahead and set up our BCE. Our first step for most types of problems like this is going to be have a BCE and then take a given and go to the correct unit. So nitrogen reacts with hydrogen, and you'll notice that I'm making these diatomic because these are diatomic molecules to make ammonia. NH3 is ammonia. To balance this out, you need to put a 3 here, a 2 here. Make sure you can see that. So we have 2 nitrogens, 6 hydrogens, 6 hydrogens. Whenever we start with our LR, our limiting reagent, we have 9 grams of nitrogen reacting. We can't do anything with grams. We need to go ahead and go directly to moles of nitrogen. 1 mole of diatomic nitrogen weighs 28.0 grams of nitrogen. And then I'm actually going to see theoretically how much ammonia should I be getting here. So I'm going to use the mole ratio of 1 to 2 here. So I'm going to put 2 moles of ammonia on top, 1 mole of nitrogen on the bottom because of the BCE. So far I've canceled out grams of nitrogen, moles of nitrogen. Since this unit here is in grams, I actually need to go ahead and go to grams for ammonia as well. So 1 mole of ammonia is 17.0 grams of ammonia. Alright, once I put this in the calculator and I put it in the calculator correctly, I should get 10.9 grams of ammonia. And I'm going to go ahead and label this on my paper as theoretical yield. And this makes sense because theoretically I should attain more grams than what I actually did. So that makes sense. Alright, so using the formula given, we got 8.70 grams is actual yield over 10.9 grams times 100 to give us percent yield of 79.8%, which isn't too bad. And I'm leaving this out to, I have right here 3 sig figs, but that's not correct because I know that I have 9 grams was my significant figures, 9.0 grams. I should record this to 11 grams, but I didn't want to because of rounding error. So when I do round this, I take my 9, I look at the next number, I see that's an 8, so it should round up. So 80 point is what I want to write to make that 0 significant percent. Okay, last problem. We've got a formula here, or a question that's going to allow us to write some formulas. Zinc and sulfur react to form zinc sulfide. If 25.0 grams of zinc and 30.0 grams of sulfur are mixed, how many grams of zinc sulfide should be produced? How many grams of excess reactant should remain after? So here we have 2 questions, and if you've never seen this format for limiting reagent problems, you should really like it because it's quite helpful because it answers many questions at one time when you do all your workout. If you've done the have and need method, that's also a way that I've done it in honors chemistry. I will not do that in AP chemistry because this method is more useful. All right, so first off, we have zinc and sulfur. So we have zinc reacting with sulfur to make zinc sulfide. Zinc has a 2+ charge, sulfur has a 2- charge. There we go. It's a 1 to 1 to 1 mole ratio. This question is going to be very easy for you in terms of math. So this is how I write this. I have 25.0 grams of zinc and I have 30.0 grams of sulfur. Grams is useless for us because we actually can't go straight to grams of zinc sulfide. We need to go through moles first. So I'm actually going to convert both of these to their individual moles. So 1 mole of zinc weighs 65.38 grams. That's a 38 grams of zinc. When I do this calculation right here, I get 0.382 moles of zinc. Same thing for sulfur, except sulfur, 1 mole of sulfur weighs 32.06 grams of sulfur. And when I convert that, I get 0.936 moles of sulfur. Okay, this is what you have to do in your head. You see the moles that you have. This is before the reaction begins. The moles that you have of zinc, the moles that you have of sulfur. The trick to this is taking this number and dividing it by its moles or its coefficient. That's a 1, so that's going to be 0.382. This number divided by its coefficient, that's still 0.9 or 0.936 moles. Whoever you have less of here is going to be your LR. Obviously, it's the 0.382, so I'm going to go up here and label my zinc as my LR, my sulfur as my excess, so I don't forget. Okay, so since the LR should be, the limiting reagent should totally be demolished, there's none of it left. During the reaction, this is DR, during the reaction, I'm going to take away all of that. So minus 30 or 0.382 moles of zinc. And since this is a 1 to 1 mole ratio, I'm also going to minus 0.382 moles of sulfur because it's a 1 mole of zinc per 1 mole of sulfur. Before the reaction started, we had 0. So before reaction, we had 0 zinc sulfide. During the reaction, we should be adding products. So you'll see that I minused on the reactant side and I'm adding on the product side because I'm making products. So this is also 0.382 moles of zinc in a 1 mole of zinc sulfide over 1 mole of zinc produced, and I'm not writing out the stoichiometry here, I'm just writing out the coefficients. So I should have 0 of this left, something left of this, but this is my question. I know that I have 0.382 moles, 2 moles of zinc sulfide produced. The question actually said how many grams, so all I need to do here is take my molar mass. 1 mole of zinc sulfide weighs 97.44 grams, and when I multiply these two things together, your answer is equal to 37.22 grams of zinc sulfide. And you will get exactly the same answer if you use the have-need method. I prefer this method because it's more organized for me. All right, so how many grams of zinc, of the sulfur, which is the excess reactant, should remain afterwards? You've already got all of this set up. When you do the subtraction, 0.936 minus 0.382, you should get 0.554 moles of sulfur. Last step is taking it to grams, so 0.554 moles of sulfur, where 1 mole of sulfur weighs 32.06 grams. That's going to give you 17.76 grams of sulfur. And that is your final answer. Making sure if you do the have-need method, you take what you have of sulfur minus what you needed of sulfur, and that's going to give you your excess sulfur, or what we call as left. So that's going to work out the same way, giving you the same answer. Alrighty, this is it for limiting reagents for now. Know this method. This is a very important method. We will use it a lot. So maybe try, if you need to re-listen to this video, this one part might be a good idea. And I call this the before reaction, during reaction, and after reaction method, or before, during, and after reaction. All right, if you have any questions, let me know.